Cast is now starting. All attendees are in listen-only mode.
Hello and welcome everybody to today's webinar, National Electrical Code 2020, On-Site Power Generation and Distribution. My name is Lane and I will be the moderator for the day. We'll be starting shortly, but before we do, I would like to remind everyone that it is extremely important to be logged into the webinar on your own device using the specific link that was sent to your email. The link that was sent to your email is specific to your name, so by using your own device and login, Half Moon Education may verify your attendance in the event that Half Moon or you are audited by any licensing board. So if you are sharing a computer, listening in with someone, or for whatever reason are not logged in on your own connection.
This class was written to kind of track my own journey from not knowing very much about electrical installation to becoming a solar installer. And eventually I needed to become a licensed contractor, become an electrical contractor. And it turns out that in many states, if you're already an engineer and you pass the master electrician exam, then you can be a master electrician in that state. And so that can be useful for many reasons. As engineers, you're asked to be a project sign-off, but that can also, particularly with the advent of solar and batteries, result in engineering managers managing electrical scope without having ever gone through a comprehensive introduction to National Electric Code. Now, that goal of covering all of electric code in 6 hours is not feasible. And so this class is a comprehensive introduction to code, a read through of code. But what we're going to do along the way is highlight or really just focus in on the aspects of code that have to do with on-site power generation and distribution, looking ahead to solar and batteries. So by the end of this class, tomorrow in part 2, we're going to be talking about code specifically related to solar power and interconnection and batteries. But what I've found is if you just start with those special sections because you want to get a solar industry certificate and you want to know you're managing solar projects and you have to start somewhere, so you just start with, what do I need to know everything about solar? What you miss out on is an appreciation for the more general sections at the beginning of electric code, which govern basic things like conduit and cable and fuses and breakers. And it'll limit your solar design if you never go and revisit that initial generalized section of the beginning of code. And what you can also discover is if you have a solid appreciation for the general principles of National Electric Code, the specialty conditions you no longer need to memorize. You can say, okay, well, normally it would be this, but I know this special thing about this special device, and so I'm going to have to modify it from what's normal. You don't need to memorize all of code. Basically what code boils down to is a bare minimum safety measure. And so if you can reason through electrical safety, then that goes just hand in hand with National Electric Code. So one of the main things that we need as engineering managers or architects is to have our visions become reality. And solar costs have come down substantially over the last 10 years. There's other things involved, but to have our solar projects be stunning, to incorporate solar into the building and not just have it be up on the roof, to push the edge of solar design, you can't do that without a strong understanding of the fundamentals. Now, the National Electric Code is actually a private organization, and that makes it hard to teach a class on National Electric Code because we can't, give you a copy of code and we are supposed to have by reference only with code. So even in a code class, things like handouts and become a little complicated. So just know that the way code works is a private organization maintains it, and then local governments choose to adapt it or not. So there's certain states like Mississippi that aren't officially on National Electric Code, and then there's other states that require the latest and greatest National Electric Code. All right. There's no problem designing to the highest safety standard, where NEC 2020 is at. Code, most of the code is there for a reason. In fact, as we get to know code, we'll see that it's not rigid. It's a flexible tool. It's not trying to establish a maximum safety standard. It's really trying just to define what a minimum safety standard is. So let's start off with some 2020 changes. The first one, these are directly from the NFPA website. The first one is that code is consolidating to make it easier to find the information that you need. What we find is that code evolves. There used to be a small section on batteries, but now batteries are very different than they were just 10 years ago. And now there's a section on high voltage batteries that we'll get to tomorrow. So there are redundancies in code. You can be, if you just do a start to finish read through of code, you'll see the same phrases appear over and over again. You're like, I thought I just read that, and basically code repeats itself a lot, and then people get fed up with it, and then they try and do some consolidation. So that always occurs. This is the main one for NEC 2020 with regard to solar power, is the requirement for an exterior emergency disconnect at dwellings for emergency responders. And this has always been a debate about where the disconnect locations are on a solar job site. And it's had its ups and downs. A lot of utilities have stepped in and required these external disconnects. Independent, code just requires a disconnect. A breaker is a disconnect. So solar lands on a breaker, that's your accessible disconnect switch. Utilities have said, no, that's not good enough. We need a disconnect switch that's outside the house, and then often it turns into a knife switch. The code has now come down and said we have to have a switch on the side of the house that can de-energize the solar array during an intentional power outage. So if there's something going on in the building, the emergency responder can kill solar power, and that has to be outside the building. The main thing with these emergency disconnect switches is you need to lock them. And that becomes a logistical issue. Does the installer lock it? Then you give the keys and the lock to the homeowner because the installer doesn't want to ever come back on that job site when they're done with it. But if you don't lock your exterior disconnect switches, they become safety hazards themselves. People can open them up, stick their hand in, and electrocute themselves. So that's the main safety concern about these emergency exterior disconnects, is to make sure that they are locked up at the at commissioning, or when the grid side is tied into the top of that disconnect. Some other, there's expanded code on Ethernet cable. Another big one is updates for load calculations, namely with lighting load. So in code, there's parts where you can say, I need to plan for this many watts of power based on the building being for this use and this square footage. And those lighting loads were based off of incandescent light bulbs. Now we have LEDs, which are 80-90% more efficient, and so that's been updated. Introduction of requirements for the safe use of electric vehicles as backup or emergency power sources. I think that is a major step forward in National Electric Code. And what we see, just to kind of spoil the battery sections for tomorrow, is that they're breaking out code to say, okay, there's a difference between a manufacturer product like the Tesla Powerwall and a product that an installer assembles together out of a myriad of parts to have a code compliant system that way, but it's not a manufacturer all in one. So they're giving complete assembly listed assemblies more flexibility in design with harsher requirements for something that's been kind of tinkered together, which makes sense. But the big thing was that your batteries had to be listed for use. And so could electric vehicle, batteries intended for an electric vehicle actually be wired up to a home and used for home safety load? That is something that International Building Code has allowed, but not National Electric Code, which it took a more kind of murky response on it. So now we see kind of permissions to use electric vehicle batteries into the building starting to come into the building. So that's important because electric vehicles are the number one source of batteries, much more so than on-site storage, even though you could argue it would be better for the battery to stay in one place. And at any rate, the electric vehicle market's driving the battery market. And so what do you do when the batteries for cars have worn down to the point where they don't make a good car vehicle or they're getting swapped out? One answer is put them to use on a building. Is that allowed by code? Code's taking steps to say it's allowable. Okay, so we talked about how code is this kind of repeating pattern. The actual structure is we start off with definitions, very general stuff that you could read through and say, okay, I get most of that. Then we get into wiring and protection. This is one of the main sections of code for solar design. Wire ampacities, service entrance sizes, ground wire sizes, things that have to do with on-site power and distribution in general show up in that section. After we introduce how power is brought into the building and distributed through through our electrical services, we're ready to better define the wires themselves. So after we talk about grounding and power distribution, then we get more into specific kinds of cables. What differentiates a indoor cable from an outdoor cable, temperature ratings, voltage ratings, and also the stuff that the cable goes into, metal conduit, versus a metal net, or outside a conduit, or plastic conduit versus metal conduit. So already we're seeing kind of a rhyme and reason to code. They start out very generally with fundamentals of electricity coming into the building. Then they talk about the wires, and then they talk about the equipment that it powers. So section 400 used to be kind of the equipment section, and then everything else is kind of tacked on to say, okay, well, there's some buildings are different than others, so there might be special rules for assembly buildings versus homes. And then we see this specialty equipment section towards the end that has defied the downward trend and instead is growing and size, what happens is there might be references to general equipment such as batteries that all of a sudden technology changes and they become more important, and so they add on special use cases. So a lot of solar battery stuff has their own section in section 600, but it might have some redundancy in section 400 as well. And then we get into 700, which governs batteries and interconnections, and then 800 is like Ethernet data cables. So thumbing through the code book, most of the time you're actually thumbing through the first half, and usually, in terms of cable sizing and ampacity and derating, that's going to be in section 200. But if it has to do with conduit or wiring, it'll go into section 300. Okay, let's talk about some, section 100, some definitions. Accessibility is capable of being reached for operation, renewable and inspection. Readily accessible is even more accessible than that. So, if you can reach the disconnect, but you might have to have a step stool, that's an accessible disconnect. A disconnect that's, 6 feet up or 8 feet up the wall, where maybe you're stacking a whole bunch of equipment up a wall, and some of the inverters require accessible disconnect switches. You can't quite reach it, but you could with a stool. That's okay. Readily accessible is different. It's heightened. It says, without climbing or ladders. This was a term that threw me for a loop when I was looking for like special cases and exceptions. It'll say utilization equipment, can do this or that. Like, okay, so is utilization equipment utility equipment? Is power generating? No, it's utilization equipment is equipment that is being utilized, a load, a device, non-industrial machinery, washing machineries, air conditioners, appliances are utilization. Generators are not utilization equipment. Solar arrays not utilization equipment. AHJ stands for the local authority having jurisdiction. So remember, the AHJ is the one saying we're going to use National Electric Code. So they have final authority to override National Electric Code or change it or add to it. And usually when AHJs add requirements to an installation, that at the bare minimum, that means they have a department that's looking into the subject matter, and they might have a little more flexibility than code does. So if a issue does arise that needs attention, they can step in and implement it without having to wait for National Electric Code. So one of the main instances that I've come across is in like New York City row homes. They can require more robust conduit sizing. A conduit like intermediary conduit or rigid conduit instead of a more flexible EMT conduit, out of concern that, hey, these are buildings that could cause, a whole lot of fires, not just the one house, but everything else, all the houses down the row, so they require tall buildings, they might require better conduit protections. Bonding is what you would think of as grounding when things are grounded together, but it's not touched the ground yet. So, the ground is really like the, you want your during a fault, you want to be able to control where that electricity goes. You want breakers to be able to open, you want loads to be able to disconnect. And if you just had everything connected directly to ground, there's certain instances when you want to do that, such as extending the ground from the building up to all the metal non-current carrying parts. But as far as the circuit itself, you wouldn't want the circuit to be grounded. And so you have a return path for that electricity to go into the load and then out of the load. And how that return path is bonded to ground creates the flow of electrons. But we don't want that flow of electrons just to occur anywhere in the household, such as it would during a fault. And so, we see the term bonding to denote when we're connecting, two pieces of metal together, and then eventually that might be connected to ground, or it might already be part of the ground, but it's not as specific as the word ground is. Continuous loads are loads that would be on for 3 hours or more. Non-continuous loads would be loads that would be on for less than 3 hours of like constant operation. And then another one is the term dead front, which is the name for, when you open up a service panel lid, but you can't see inside the panel, that shield between you and the breakers is a dead front. And so I've found that term is useful to know, because sometimes a disconnect switch may not have a dead front, and a local inspector will say, hey, I want to see this, with a dead front. Okay, so under the concept of continuous loads, which of these loads would be continuous and which would be non-continuous? Really what's important here is solar a continuous load or a non-continuous load, because the sun is not up all day long. But a solar array is on for 3 hours a day or more. A solar array is a continuous load. A dishwasher is not on for 3 hours, straight, but an air conditioner and a refrigerator are. And so, out of all of these, I'd say the dishwasher is the non-continuous load, and the rest are continuous loads. I'm going to start picking up the pace a little bit. A branch circuit is what electricians call the circuits in your homes, but there's a certain kind of circuit called a feeder, which transfers, power from one distribution panel to another. So, many small homes just have one, service panel, and there's a feeder circuit going into that panel from the utility, and then branch circuits coming out of it. But on larger facilities, you might have a series of disconnect switches feeding a series of distribution panels, and that would be a feeder circuit. Now, what's interesting to me about this is an air conditioner on the side of a building is usually on a dedicated circuit. And so if you just wire the air conditioner directly up to that, then the circuit could be considered a branch circuit. But if you put a service panel on the outside of the building where the air conditioner is, that could be considered a feeder circuit. So solar arrays and batteries, they're not allowed to share branch circuits. You're not allowed to plug a solar array into the wall. You're not allowed to share the same circuit as non-related loads. But you are allowed to connect to feeder circuits. So, under the right design for a small solar project, it's perfectly acceptable to take that internal wire run that's already been made between the air conditioning unit and the service panel, and where the wires come out to feed the AC, that can be a point of a convenient point of interconnection for a solar array. Charge controllers are DC to DC devices rather than DC to AC devices. So used to be quite common, but a charge controller charging, this is a DC device. Um, let's see. We have the difference between tubing and conduit. Basically a tube is something that's fully enclosed. So most conduits are tubes if you had to really get down to it. The type of enclosure can be similarly specific. There's fences, full enclosures, enclosures that are just intended to prevent accidental contact, and then enclosures that are needing to be fully enclosed. And then fittings are the general term for all that balance of system electrician stuff, the little brown piece on the Tinker Toy set that everything plugs into or connects things together. And all of this stuff, the fittings, the bushings, those connector points, that can be the hardest part of the design, is to get those correct. Knowing how to specify that material can be incredibly valuable to project logistics. It can be the difference between very expensive turnkey contractor and savings resulting from dividing the scope up and doing a little bit more on the design end. Other important terms, the effective ground fault path is the path that the electricity is supposed to take if there's an electrical fault. That doesn't mean the electricity always takes that pathway, but if we're, the point of the equipment grounding system, when you see that ground in the side of your wall plug, the point of that ground is so that if there is a problem right at that outlet, that the electricity has a place to go and clear to ground. Otherwise, it might be going somewhere else, like into your non-related metal devices and arcing further than it should and causing a fire. Let's see. Then we have a grounded conductor. This is the weird thing. If you don't have a solid understanding about electricity, is we think things in terms of being like on and off, but it's really more like being on top of a mountain or being at the bottom of the mountain, having a lot of potential energy or not having any potential energy, and you need that difference in voltage potential for electricity to move. So we hear about, birds being able to sit on power lines because there's no voltage potential between them, so they don't electrocute themselves. Okay, but the way that we get electricity to work in our circuits is, the electrons need to flow from a high potential to a low potential. So the return path for electrical flow in AC wiring is the neutral. And the neutral wiring is intentionally connected to ground in order to create that voltage differential so the electrons can flow from the hot legs, to ground. Now that connection, that intentional grounding, is only made at one point, because we want a funnel. We don't want a sifter. We don't want the electrons just to flow out any direction. And in fact, there is a kind of a drain, would be an analogy. The final ground on a home needs to be a lot larger than the ground paths for the effective ground pathways for the individual devices. So all the effective ground paths do eventually stack up and get larger and larger the further you get towards your point of interconnection. We're going to talk about arc faults and ground faults and fault protection in just a minute. So we're going to kind of just leave the rest of this stuff for your reference. So let's talk about arc faults and ground faults. In the news, I guess as of last year maybe, Walmart sued Tesla to get out of all of their Solar City solar leases. And that could be a huge loss, if it went through, because a lot of these solar leases were crafted at a time when there were excessive solar subsidies. And so the lease value, and solar was more expensive a few years ago than it is today too. But a lot of the lease values, what made a really profitable project a few years ago was the combination of the subsidies, and the declining costs. And to make a lot of money off the projects, Solar City would just take whatever they could, share the least amount of profit with the lessee because they want to keep the money. Well, if you cancel all the 22-cent a kilowatt hour solar leases and replace them with 5-cent a kilowatt hour solar leases, that would be a huge financial loss for Tesla. So I can understand why Walmart, looking at the value of solar leases today, they're saying, I want to get out of these. How do I do that? And all it takes is a couple fires breaking out for them to say, that's our, that's our outlet. Now, this case was later settled, but at the time, the Tesla was wanting to blame the manufacturer of this connector, and that was never that argument was never held up in court. What is much more likely is the installer can mess up this connector in a variety of ways. These MC4 connectors are the weak point on a solar project. If you take any electrical wire under load and you disconnect it, that electricity, as that cable is being pulled apart, is still going to try and jump across this air gap. And so when you get a fault between one cable to the next through the air, that's an arc fault. And arc faults don't need to occur just in an air gap. Any loose wire terminations where the nut or the bolt is not torqued to the manufacturer's spec can cause arc faults. Stranded wiring that is poorly secured onto a terminal can cause arc faults. And back in the day, inverters did not have arc fault detection in them. And so perhaps the reputation of solar inverters for being string inverters for being bulletproof was, to some regard, hiding some workmanship issues of installers, because an arc fault can be occurring with the equipment still operating. If there's not much arcing, just some arcing, the rest of the electricity is still going through the circuit. If your inverter doesn't have arc fault detection, you could have a workmanship issue on the roof starting to catch a fire on your roof, and you wouldn't do anything about it. Now, as in other industries, but particularly true with electrical industry, it comes down to good workmanship. And particularly on commercial projects, you should have electricians do this work. But there's other aspects of solar that are not electrical work, and it's labor work. So generally, what I do is I get the most experienced worker to make up these MC4 connection points. So an arc fault jumps between two gaps. Just some final detail. You got to make sure that crimp is right. You got to make sure that it's tightened up around. This connector is tightened up tight. And then you also have to do good cable management. You have to make sure that this connection right here doesn't drop down onto the roof deck, which could later become saturated with water after it rains. And so here's a solar project on a flat roof. And, it looked like a pretty good project, but what we discovered getting into it was that the roof was lower than the drains on the roof. Well, that's weird, but this is an old building, and the roof had been put on and taken off a couple of times. And for whatever reason, the drain pipes from these roofs were sticking up out of the rooftop. And in fact, I guess you can't really see it in these pictures, but there was a little, in order to seal the penetration for the drain pipes, they had to build up that section of the rooftop, and it resulted in a little levee surrounding the drain. And so every time it rains on this rooftop, the whole frickin' roof turns into a lake of water. Now, look, I think that putting a solar on top of a roof like that is not a good idea, okay? But as the contractor, by the time we're discovering that, it is what it is. And so what you have to do is make darn sure that all of your cable management is keeping these cables, nice and tightly wrapped around these module frames. What you can't have is these loose MC4 connectors, sitting in a puddle. Because if it's sitting in a puddle and water's getting in there, you could have, for that has potential to be, a ground fault issue. So if you have energized water and you step in it, is that going to be a ground fault or is that going to be an arc fault? So an arc fault is between two wires that are kind of pulled apart. A ground fault is when that electricity, instead, makes a connection to ground. And so if you have an MC4 connector in a puddle and it's on an insulated roof, and then you go and you step on it, hey, maybe nothing will happen. But if that puddle goes up to, the metal on a piece of equipment on the rooftop and that metal's connected to ground, then you would have a ground fault. And maybe that ground fault is actually what you want. Is a ground fault a bad thing? Well, it can be. It can also be an indicator of a larger problem. Well, what we have to do is better understand the limits of these systems for detecting ground faults and arc faults. But being able to diagnose the difference between a ground fault and an arc fault can help you figure out what the cause of it is. And so here we have two wires that are landed on a terminal block, and we want to figure out what's gone on with this issue. And so what we have here is this is the AC terminal block. So this is going from the grid into the block. So the question is this an arc fault or is it a ground fault? And here's the neutral conductor. And that looks all right. What we have is leg 1 and leg 2 of power. This is the two. You don't have a positive and a negative coming in from the grid. You have a leg 1 and a leg 2 of equal but opposite 120 volt AC sine waves. And that makes a 240 volt potential across them. And what happened here is to me, it looks like we got some arcing between the leg 1 and leg 2 conductors. And so one thing that I think do-it-yourselfers should take under advisement is that these terminal blocks for these power inputs are right next to each other. There's not that much space between them. So if you get things wrong, like stripping too much wire off of the end of the cable, on an AC breaker panel, things are a little bit further spaced out than in a solar equipment, and solar equipment is quite expensive. And so what this was basically a $3,000 piece of equipment that was bricked because the manufacturers are not compartmentalizing their control boards and letting you take a control board and put a new one in. They swap out the entire unit. And that arc fault was caused by stripping too much cable off of the conductor and it arcing because it's right next to this other conductor. So, poor workmanship. And I'd say that is what most problems are on a solar array is poor workmanship. So take that in mind when you're selecting an installation contractor or considering it do it yourself. These manufacturers specify exactly how much, and it can be a different amount at different terminal ports on the inverter. So that's all stuff that you find in the installation manual, but you have to follow it, or at least make sure that whoever's stripping the cables is looking up the terminal links and getting them right. Let's talk about system grounding. We're going to take a break at the 1.5 hour mark, so we still have a ways to go. Aren't you lucky? This ground wire, this green ground wire here, that is our effective ground fault path. If something goes wrong, if a meteor rips a hole through the panel in the microinverter, and now it's just empty space and silicon and the sun's up and there's no clouds in the sky, and so things are it's a really bad day. Probably have to deal with a meteor, but that lands in the swimming pool, and now we have the solar array to take care of. What the goal of the effective ground fault path is to take that electricity and shuttle it into ground. Normally, that electricity would be flowing through the neutral back to the service panel, and then there's one point, and it can be inside the meter or it can be at the service panel. But there's one point where this neutral wire is connected to ground, and that gives the electrons the ability to flow. And of course, your ground has to be actually grounded too. There's this other part of the ground system, which I've been calling the drain, which is really called not the equipment ground conductor, which is the effective ground fault path is the equipment ground conductor. This green ground fault path is sized for this equipment, for this circuit, going back to the service panel. And then based on the total size of the service, the drain is sized and makes that connection to ground. So we got the equipment ground conductor that then feeds the grounding electrode. We're going to talk about that in a minute. A ground rod, a ground plate, a whole bunch of copper wire thrown into the ground. Whatever is your grounding electrode technique, there's a few of them. There's a special term for the very last ground in the stop, which is the grounding electrode conductor. And I don't know, sometimes that needs to be a little bit, 400 amp services needs to be a little bit larger than a 200 amp service. So keep that in mind. So how does a breaker work? When there is a ground fault, how does a breaker know that and interrupt that? Well, there's a couple of different, not all breakers have ground fault detection built into them. That GFCI breaker is the one with the little push button on it. Not all the breakers on your service panel have that. So what do regular breakers protect? Regular breakers are your overcurrent protection. If this is a 40 amp breaker and you got 40 amps going in and 40 amps coming out, and this is a 40 amp rated breaker, once this breaker goes up to 41 amps, this breaker should trip. So how does it do that actually? Well, it basically uses the heat from the wire to physically, this coil moves, expands and contracts with heat, and that expansion drives a lever that literally opens up the switch. So it's heat driven based on having too much current flowing through that conductor. So it's just an overcurrent protection device. And so we have breakers to make sure that if our devices are malfunctioning in a way that they're pulling so much power through that it would cause the cables themselves to start burning up, then the breaker trips. If I'm taking a device that is malfunctioning, and normally it should be drawing some power, but for whatever reason it's drawing twice as much power, the breaker will trip too. If you take a device that is leaking a little bit of power but not all of its power, a regular breaker won't have the heat necessary to open up and pull it apart. And so what a GFCI breaker does is it inserts a computer chip into the board, which is very ironic because National Electric Code really likes manual switches as a matter of principle, whereas European codes, you're less likely to get this aspect of the breaker because they say this aspect of the breaker is good enough. And so European service panels are cheaper and smaller and in many ways more tidy. American products are bulkier, more expensive, but they also have the added benefit of this, mechanical switch. But back on the GFCI breaker part, just like an electrician has a clamp meter where they can clamp around a wire and monitor the current flowing through it, the breaker is monitoring the current flowing through the return of the circuit. And if it notices a fluctuation in the return that is less than 40 amps or 20 amps, so it might only be 0.1 amp or 0.2 amp, depending on how sensitive the device is, it can trip the ground fault and turn off. So where it's using, circuitry, computer chips, computer boards, science, not just brute heat to detect lower amperage ground faults. So I think the important thing to keep in mind is just a regular breaker by itself is only for overcurrent. It's not for instances where it's undercurrent. It's not for arc faults. And for that reason, the inverters today are listed for arc fault detection and ground fault detection. They didn't have those features when they were first starting out. So by and large, you want to assume that a breaker trips for a reason. If I have a customer call me and they say, well, the breaker tripped on the solar array, I don't want them to reset the breaker and just see if the system starts up again. A better process would be to give the system a visual inspection to see if a fault occurred because of something not going off. But in this case, the inverter didn't flag an error when just a little tiny arc connected the two together. And the breaker only tripped when you got enough current flowing. So anyway, the problem occurred without flagging, without really flagging the issue. I don't know if I said that right, but the breakers don't trip for no reason. It's very rare to have a breaker that's tripping because it's at the end of its life and the coils are expanding at 35 amps instead of 40, and so it's tripping when it's not supposed to be, as an analog breaker would. But also, not all breakers can detect all kinds of faults and prevent all kinds of faults. All right, so picture is worthwhile. What we can see the heat from the cable. Amperage is a heat issue. Voltage is more of an explosive issue. And what we're seeing here is signs of melting rather than pulverization. This is an amperage issue. And arc faults can naturally occur when you have an energized load and you flip that breaker and you have a disconnect. You'll have an arc fault. Arc faults can precede ground faults. So if you drive a nail into live electrical wire, it may just arc fault. And that might be I would hesitate to say it's less of a safety issue, because the heat from that arc fault can cause a fire. Also, the power quality from the circuit to the device can cause the device to fail. But generally, you'll have arc faulting that then finds a path to ground and becomes a ground fault. I kind of want to get to section 200 and start talking about ampacity. We have island mode to describe a microgrid. This is kind of an interesting one. Interactive system intended to operate in parallel with the electric utility. And to me, in the non-electrical engineering world, I'm thinking, well, two parallel lines are running side by side to each other but never touching. But they're meaning paralleled series wiring versus parallel wiring. When you're AC coupling inverter to the electric grid, which is basically when you're connecting any inverter to the electric grid, that's an interactive system. And says to supply common loads that may deliver power to the utility. There are one-way inverters that don't, at that point of interconnection to the grid, feed any power out of that point. It might just be a one-way charger, and the inverter might have a separate output somewhere else for feeding a critical load panel. So like a UPS system, a battery system that protects your computers when the power goes out, that's a one-way inverter that charges from the grid but has a separate output. So a battery charger for your power tools has a battery and an inverter, but it's one-way electrical flow. It's not interactive. You can plug that into the wall and charge it. An interactive inverter is one that can output power to the utility. Dry locations and wet locations are pretty obvious. Maybe what's less obvious is slabs or underground would be a wet condition. Damp is a special wet condition where it's protected and under some awnings, and that can be useful in solar. There's a cable that I like called MC cable. It's a metal clad cable. We'll get to it later. But MC cable specifically is only rated for damp locations, so it can't go. There's only specific spots where it can be outside. And what that means is if you're coming out underneath a soffit, you might only have a couple of inches on the outside before you have to go into a box so that the soffit is still protecting that cable. And if you're in a very rigid jurisdiction, you might have to make that transition before you come out of the soffit, although, you know, flexibility does have its uses. And so you have to know, like, is the attic a wet space or a dry space? You know, the attic is considered a dry space. You know, right above the attic is considered a wet space. And so you have to take that into consideration when you're transitioning from the dry space to the wet space. You know, you're putting in good sealant for one. You know, solar is a hot environment. It's a wet environment. It's electrical equipment, so it needs adequate service space and clearance space. It can be hard to fit a complete solar system with a solar array and a battery in a control room because of the clearance requirements. So anyway, rather than just read more vocabulary, we're gonna come back to this. Well, okay. I guess we need to do a little bit more highlights. Let's see. NEC defines used equipment as reconditioned equipment. So that's pretty interesting because actually the commercial solar tax credit can qualify used equipment for the tax credit, provided that only 20% of the equipment is used, 20% of and 80% is new. So there's kind of a reconditioning or refurbishment that is built into code and also comes up in other arcane rulemaking processes. Sealable means, capable of sealing or locking so that live parts cannot be accessible without opening the enclosure. All right, let's get into some more pictures. All right, so installation requirements. Equipment that is listed, labeled, or both. So the important thing is listing and labeling are not exactly the same thing. Labeling, the requirement might just be to field label it, to say, hey, add this information to whatever you installed. Whereas listing would say, hey, whatever you installed, has to be specifically called out to be for this purpose. So a slight difference in nuance between the two. Installation torque values, they're putting in code, an approved mean shall be used to achieve the indicated torque value. So this is a big update. Basically it says you have to have a torque wrench on site to complete your cable termination torquing. And I would say not all solar installers have torque wrenches on site. They rely on their, I use my hands and I know what a tight connection is. Code now says have a torque wrench. Okay, working space. I don't memorize all the working space requirements. Basically what I do is imagine a person standing in front of the equipment working and to say, is this comfortable or not? At first glance, it could seem like this air conditioner is sharing the same spot as the electric service panel, but it's actually not. There's a 6.5 foot dedicated space vertically for your electrical equipment from the floor, or from wherever it starts. And so 6.5 feet up, really the only, aside from, how some of this data cabling and stuff looks, the code violation of this room is actually the buckets that could be easily moved. You have to have dedicated space for your electrical equipment so that you can stand in front of it and work in it comfortably. A lot of code violations are, in terms of planning, are readily apparent to visual inspection. Here is a box, and you have to lean over some batteries, which kind of have, they have some, shelter on them, but no bones about it. These are live terminals right here and right here. And you have to lean over those terminals to access this panel. And okay, on the one hand, it could be easy to see how they got here. They just had a very limited amount of space, but that's a safety hazard. So in code, it says you can only have a 6-inch relative depth between one piece of electrical equipment and another piece of equipment that's above or below it in that same space. And so I don't know, sometimes that can come into a room layout planning, like if you have a gutter and equipment that sticks out far from the wall, you may need to have the gutter offset from the wall a little bit. Mainly what I see is with these floor mounted batteries, like this case, you got to watch out for. So 6-inch depth, 6.5 feet height. The width requirement, this is the easiest one. The width of the space, it almost never becomes an issue. The only issue would be outside, is if you have like a gas meter and you're up against the wall or the edge, how far apart from the inverter can you land that gas meter? There's, as far as the electrical side goes, and some jurisdictions have larger requirements, but as far as the electrical side, it says 30 inches of dedicated space, or the width of the equipment if it's any wider than that. And so how I remember that 30 inches, again, it's just what could one person standing in front of the equipment, so a terrible person, but 2 feet is not enough space for a person to squeeze in front of that electrical box and do any work. They need to be able to stand in front of it and work on it safely. It's about 30 inches wide. It's not 3 feet wide. Electricians are not 3 feet wide, but they need more than 2 feet. That's 30 inches. 6.5 feet tall, not leaning over more than 6 inches. The one that can be a little bit tricky is the depth requirement. Not from sticking out relative to other pieces of equipment, but from the dedicated kind of floor space that you need without something being behind you. And it's really weird because the rule is if you don't have anything behind you, then that depth is 3 feet. And so if there's nothing behind you, you need 3 feet of clearance space. It's like, well, if there's nothing behind me, I have infinity clearance space. Okay, well, that means like things like those mop buckets and stuff can't be within 3 feet of the panel. However, that becomes a larger requirement if there is something behind you. So code says if there's nothing behind you, 3 feet, but if there is something behind you, we're going to step up the requirements. And actually, the requirements are different if it's 150 volts up to 600 volts, such as, so if it's a 120 volt service panel, if it's a 240 volt service panel, or if you're getting into like commercial systems. And so what I think about is I just worry about the residential requirements, and then I assume the commercial requirements may be more stringent. And so when I'm thinking about room planning for 600 volt, solar equipment and associated equipment, as far as that clearance space goes, it's 3 feet if there's nothing behind you. It goes up to 4 feet if there is something behind you. And there's also a middle condition. So there's a condition for if you're backed up against electrical equipment, or if you're backed up against an insulated wall, or if there's nothing behind you at all. And so you get into the higher ranges if there's electrical stuff behind you, and the shorter ranges if there's less stuff behind you. And so when I'm thinking about code and electrical room planning, I'm thinking about, well, what's the spaces between the equipment if we have a piece of floor mounted equipment and another piece of floor mounted equipment? Well, you would need 4 feet of space between the two pieces of equipment, because that's something that's driven by the early sections of National Electric Code. Now, you might even say, well, what does that mean for spacing around the solar panels themselves? What I can say to that is I guess the whole array is considered one unit, because there's not 4 feet of space between the individual rows on solar arrays. I like it when there is space for accessibility, but the standard is to cover most of the roof and only have walkways every 120 feet. Okay, so some other notes. We talked about the dedicated space. We talked about locking the enclosure or the rooms. We're seeing requirements about physical protection, and even more strict requirements the higher the voltages get. Once you go above a certain amperage, they start governing the way the door opens on the room that the equipment's in. Even larger than that, you might need 2 entrances in the room. Okay, so it says listed interactive inverters shall be permitted to be connected to premise wiring without a grounded conductor, where the connected premise wiring includes a grounded conductor. Well, what does that mean? Maybe it's a typo. I can't have this be a verbatim thing of code, but what I think it's saying is this. Air conditioning equipment sometimes does not have a neutral. And I said, well, you need that neutral to be the return path. Well, there's a special case, and that special case is when you have a 240 volt circuit, which is actually 2 sine waves that are equal and opposite each other, and so they always have that 240 volt potential already. And so the nature of the 240 volt potential, it's 120 volts up and 120 volts down. We have that voltage potential, and voltage can flow across those 2 phases. And because these 2 phases are perfectly balanced, and so the air conditioner is drawing its power from both phases equally, whereas you might have on an electric service panel a different load on the right side of the panel versus the left side of the panel, because they're doing different things at different times. An air conditioner is using that 240 volt circuit uniformly. And so they say, okay, well, in that case, or not in that case, in the case where it's a non-uniform load, where one load is smaller than the other, the neutral wire balances out the 2 loads. It shuttles off the difference in the load back to ground. But the air conditioning unit's perfectly balanced, and a 240 volt solar inverter is perfectly balanced, and most 240 volt devices, by nature are perfectly balanced, and so sometimes 240 volt devices don't have a neutral wire because they don't need them. And so what this is saying is that actually solar inverters that are 240 volt do not need a neutral wire, and that all the more says that this can be a point of interconnection on a home, which I think is really interesting, because what that implies is you can put a just 4 or 5 panel system next to your air conditioner, maybe backfeed with microinverter circuits, or even do a kind of a critical load panel and back up your air conditioner while also backfeeding the grid. Like, it's a ripe opportunity for smaller, kind of ambitious do-it-yourself type projects. And it's allowed by code. And so some inverters will actually have a programmable setting on them where you can say, okay, well, this is 240 volts with a neutral. This is 240 volt, without a neutral, and there's other stuff going on there too about matching the electrical load. So some inverters can be configured to work with or without a neutral. And now we know it's because they're both legs are in perfect balance. And while we might not fully understand what imperfect balance means, we can understand what imperfect means. And if one side of the inverter worked harder than the other 120 volt leg, it would be imbalanced, but that's not how it's designed to work. Okay, so number 4 cable shall be identified over 60 volts, shall be identified at all terminations and splice points by tape, tagging, or another improved means. What that means, if it's smaller than number 4, the code compliant method is to use colored wiring. So that's when you have a red wire or a black wire or a white wire or green wire. So when it's all number 6 and down. Otherwise, you're allowed to identify it by colored tape. And it says number 6, we're not serving as the connection point for a grounded conductor. What it's saying is we use red for positive and black for negative on the DC side of things. And what that means is solar installers, you can have an installer that buys they're commonly using number 10, commonly using number 8, sometimes number 12. Those solar cables, they come in colors, and they also just come on a black spool. And if you're in an area where you have a very rigid electrical inspector and inspection, usually if you're in that area or not. They have, they might have solar specific inspectors. They may have solar incentives that come with additional oversight. Red for positive, black for negative on a DC system. Just like we were talking about imbalanced load, that it's now coming back to addressing, saying, hey, we want you to distribute branch circuits as evenly as you can along electric service panels. And now we have a requirement for arc fault current interrupter protections in readily accessible locations. And so that's been a relatively new invention and device, is arc fault current detecting circuitry. And you can imagine that if it's harder to detect a ground fault than it is an overcurrent instance, then it's going to be even harder to detect a smaller instance with less amperage in terms of a arc fault. And so those breakers are new. I think more basically with breakers, we can learn a lot about sizing by just noting the sizes that breakers come in. We have smaller breaker groupings, but then as the breaker sizes get larger, this grouping starts to separate. And so when we're linking the breaker size to our circuits, we have to do a couple of things. One, we have to look at the ampacity of the load, and then we have to apply some safety factors, and then that's the size of the wire, and then we have to look at the size of the breaker. So the question is, like, if I have a load that is 16 amps, and then I put it in I size the actual load might be 12 amps, and then I apply my over circuit protection for 16 amps, and then I go and I look at, well, what's the cable size I need for that? If I go and I put it on a 15 amp breaker, that won't work. The breaker will trip. So the question is, how much do you upsize a breaker for? And you're upsizing, because you can't get precisely, a 16 amp breaker. When these options start spacing out and you start getting into larger and larger circuits, you may actually take the load and take your cable size and have the breaker be somewhere in between, so that the load interrupts before. So that the load that is possible to go through that cable cannot possibly exceed the ampacity of the cable. At any rate, we're going to start developing how to size a cable for a load. And the fundamental building block is that you size the cable for non-continuous loads plus 125% of continuous loads. And so continuous loads are treated a little bit differently than non-continuous loads. So why is that? Well, a continuous load is one that's always on, on for 3 hours or more. And so the cables of that continuous load are going to be operating at a higher temperature than that of an equivalently sized but non-continuous load. And so we're saying, hey, continuous loads have higher operating temperatures, and so they, right off the bat, they need a 25% oversize in terms of amperage. And that is just a common, if you're shooting from the hip and not flipping through your code book and identifying what the oversizing is, the general case is you take the amperage and you oversize by 25%. Now, then we're going to learn about some additional points, but basically when you apply all the special factors on top, your starting point is assuming whatever the load is rated for, you're adding 25% on top of that to make sure that the cable is not itself going to overheat. Make sure that you're giving some headroom in that cable ampacity so that when the system is at its full load, it's not overheating. So the overcurrent protection device should be not less than the non-continuous loads plus 125% of the continuous load. And so you take the continuous load, you add 25%, and then you round up to the nearest breaker size to get your breaker selection. So the cable itself is sized for 125% of the continuous load, and then the breaker is the next size up. So when you look at your breakers and you say, okay, well, that's a 15 amp load, that's a 20 amp load, and you look at your receptacle ratings and the receptacles are rated for 15 amps or 20 amps, that means you still have to put a smaller load into the actual load or real load into those receptacles. If I put a 15 amp load into a 15 amp receptacle that's on a 15 amp circuit, it would trip immediately, and it might trip, on the breaker side of it too, depending on where in that 25% extra headroom, the real amperage of the device lay. Let's see. So, there's some special exceptions, but in the interest of time, we're just going to keep moving forward. Then we have some requirements for power outlets being spaced 6 feet apart. The idea being that you're not having people use anything more than a short extension cord to power things inside their homes. Outdoor power outlets, one readily accessible outlet at the front and the back of the building. It's kind of a one that threw me for a loop because I know not all buildings have that. So then we get into feeder circuits. So we said feeder circuits are what supply a building with power. They're rated for non-continuous loads plus 125% of continuous loads. Well, it's pretty standard stuff, and really there shouldn't be much interesting, special cases going on with feeder circuits. So the neutral wire has to be in the same enclosure of, let's see, we have identification of feeders where the premise has feeders for at more than one nominal voltage. Each ungrounded conductor shall be identified by phase at all termination points, connections, and splice points. This is kind of forming the basis of labeling all of your solar boxes, because that solar circuit, I would call it a feeder circuit. They call it a special photovoltaic output circuit, but still you have to label the boxes and the conductors. Feeder circuits have to be similarly kind of over-labeled. So we have a definition of voltages, and I would just remind you that when we talk about voltages, we're talking about nickname voltages, and the actual voltage versus the nickname can vary rather substantially. It's common for rural electric grids to operate at higher voltages than this to get 124 volts per leg and get up to 248, sometimes 250 volt readings. So these voltages are kind of nickname voltages. Likewise, we're not too concerned about math. National Electric Code is a cheat sheet for making real engineering calculations. So we're not worried about significant figures or anything like that. It's where we're overestimating the safety requirements in order to enable just regular electricians to pick out the appropriate material without being engineers. And similarly, fractions of an amperage can be rounded to the nearest whole amp. On a label, when it says you have to list the volts and you have to list the amps, you don't list the decimals. You just stick to whole numbers. And so here we have some general lighting load calculations. We kind of talked about this in the changes. But basically, if I'm designing a home, and I want to start estimating what its energy usage is, I actually don't do it this way. I go find, electric bills of similarly sized buildings and kind of go into it that way. But there are general assumptions being made at how much power per square foot particular electric loads need to be sized for. And that is useful so that you don't get thrown for a loop from one building type to another. We also see that these load calculations are substantially reduced the larger the facility gets, because it's assuming that not all of those loads are going to be on at the exact same time, and it's seeing some benefit from aggregating multiple users onto kind of one grid feed. And so these tables have been substantially updated for NEC 2020 in terms of the lighting loads being significantly reduced. So that, if you're doing generator calculations and you need to know how large your generator is, you'll go and use this table to come up with, wattage requirements for those loads. Finally, we have energy code permitted to be calculated using unit values specified in code, provided that there's automatic actions to reduce the connected load, and that the continuous load multiplier of 125% is applied. So I guess the reason I'm trying to mention this is there are minimum power requirements for buildings and structures. You might be looking at wanting to build an off-grid structure, and you say, well, batteries are real expensive, inverters are really expensive. If I just do everything perfect and select all of my appliances to keep my home power draw under 3 kilowatts, can I get away with a 3 kilowatt power supply? Can I run a house off a 20 amp circuit? The answer is no. Code requires, pretty much comes out to like 100 amp service at a minimum for dwellings, and then it goes up from there. And we even see that in later sections that we'll get to tomorrow, that way down in the specialty section at the end, when we're talking about standby and emergency power generators, that they have to be rated for the loads that they're going to supply. So it says when two or more loads are used simultaneously, when it's unlikely that two large loads are not going to be simultaneous, then you're permitted to back the smaller of the two out. The neutral load calculation. So sometimes the neutral can be undersized. And the answer is, well, why, when you're using a neutral, why can it be undersized? And the two answers would be, we've actually covered already. The first would be if you don't need it. The neutral's just there as a communication circuit. You may be able to undersize the neutral. Generally, in that specific case, what do you undersize it to? And the rule is you can undersize it to the size of the equipment ground conductor, so that it can't be smaller than the equipment ground, but you're effectively installing a secondary equipment ground conductor by having a useless neutral that's undersized. The second case where you can undersize your neutral is if you have loads on one sine wave, on phase 1, and then you have an imbalanced load on phase 2 that's not drawing as much power, And the neutral, so if we reflected that, the question is, well, the neutral, which is balancing the true loads, it doesn't have to be sized to balance, the entire load as if this phase were completely on and the other phase was completely off. We have both phases being used by multiple pieces of equipment at the same time. If we can undersize the neutral under the assumption that the net difference between the two phases is not going to be at 100% of the value between the two phases. So often we'll, in this case it says for kitchen equipment you can undersize the neutral by 30%. That's kind of in the solar industry, you usually have the budget for a full-size neutral if you're going to use it, even if you can undersize. All right, so here where I guess we had defined nominal voltages, but I think it's useful to look at what's going on here. This is the point of interconnection being made. After this, we'll take a break. But what we have in this picture are utility feeder conductors. This is from the solar array service panel, and they're hanging a transformer off the grid, and they're going to wire that transformer into these conductors. And so the grid side is at 2.4 kilovolts, 2,400 volts. And coming out of the transformer on the other end is two 120 volt legs, plus a neutral. And that neutral's purpose is to balance the load difference if there's more load on one leg versus the other. So how do we get from 2,400 volts to 120 volts? Well, the symbol for the transformer is indicating the actual copper windings that allow the electricity to be transformed from high voltage to low voltage. This is actually a cheaper and easier process to do with AC electricity rather than DC electricity, which has to be more like computer controlled rather than naturally controlled. And so actually DC has a lot of merit for being the standard electricity, but the reason why AC won out is how much easier it is to transform so that we can do things like step it up to really high voltage so that we can transport that electricity over longer distances. So these are different diagrams for different electrical services, and one thing that kind of threw me for a loop recently is I was getting into some smart home hot tub retrofitting, and I wanted to fine tune a customer's hot tub. They live in an off-grid house, so that the hot tub would only heat water using surplus solar electricity. And with Half Moon, we have a smart home load control class that we kind of get into those topics. Well, I open up the hot tub and I get into the heating element, and the heating element has two wires, and it says it's 240 volts. And so the thing is it actually ended up being a perfectly balanced 240 volt circuit split between leg 1 and leg 2 versus a 240 volt circuit that actually has 240 volts on one leg going back to a neutral circuit. So that was a little bit luckily that we was easily confirmed with a voltmeter. You can just have 120 volt services. Maybe some small apartments are on a 100 amp distribution panel that only has one of the two legs, and the next apartment is on the other. For commercial services, there's different voltages. The main one thing to look out for is they call it a Y service or a delta service, and it literally has to do with the windings of the pole mounted transformer. And so you have to, in commercial design, a really good starting point is to find the inverter you're going to use based on whether or not you're on a 208Y service or a 208 Delta service or a 480 Delta service. So now we're getting into some more definitions of feeder calculations and service calculations. And they say, well, you start off by assuming a home is going to have a 10 kilowatt load generally, and then we're going to add on the lighting circuits and the appliance circuits and any air conditioning loads and motor loads to come up with the total maximum load of the house. And the difference between that process and like a commercial complex is that the commercial complex you get to apply additional discount factors for, because we're assuming that not all the units are going to be run at the same time in the same way. Okay, well, what if the building already exists and you're doing an energy retrofit? You're allowed to throw out all of this load calculation stuff if you have actual load data from the existing building. And so sometimes your utility has this available in your electrical account. Not as common for them to have that for residential, but most commercial businesses are billed off of demand charges. So the utility commonly has demand charge records for commercial businesses that you can get from their service account or on request. So they say, well, if you have, this electrical load for 1 year, then your service needs to be able to supply 125% of that maximum load. And so that might be how you get around, if code says you need a 400 amp electric service, but for whatever reason, maybe the utility charges more for a 400 amp service versus a 200 amp. Maybe the home only currently has a 200 amp service, but you're putting in enough devices to say, well, code says it needs 400 amp service, and you're looking at a costly second wire run out to the house. And you're like, well, can't I just keep it on 200 amps if energy management is involved? The answer is yes. You're allowed to not follow these general sizing requirements if you have additional data to indicate that not all the devices are being used at the same time. We got clearances for overhead feeder conductors and outside branch circuits for not over 600 volts. If the circuit is in excess of 300 volts, you have to have a 15-foot clearance. Wow. If I wanted to have a solar pergola outside or a solar carport outside, and I'm using the standard solar 600 volt platform, that system has to be 15 feet up in the air. And then, carports to begin with over a driveway need to be 18 feet up in the air. So code actually will drive the design work of your covered structures. One workaround would be to find systems that are just up to 300 volts. It's pretty common to find a 300 volt system. Outback makes the popular solar inverter company makes 300 volt platforms. if you wanted to do kind of a pergola, but you didn't have the clearance, the height, you just use lower voltage. Above roofs, 8.5 feet clearance, except for when the roof is subject to pedestrian traffic, at which point it becomes more like the original. And so, the concept of taking like a row home and it has a limited amount of space on the rooftop, and you say, well, we could put a solar array there, or we could put outdoor patio up on the top of this tall, skinny building. And the answer might you might think, well, can I put a solar array shade structure on top of the patio? You to do it in a code compliant manner, it's going to be a very tall structure. So structural engineering requirements and local or building height ordinances could come into effect. When you're trying to learn more about electrical systems, looking out at the grid and seeing if you know what all the devices do and they're code compliant becomes kind of a fun game. But if you go into a major city, say Chicago, and you get into these multi-story buildings that line the street, you look out the window and you're staring directly at a utility transformer with tons of wires and cables coming out of it. You might think, well, is that safe? How far away can power lines go from, say, windows? And the answer is, 3 feet. The external conduit run along the side of a building, the inverter location, all that stuff has to be 3 feet away from openable windows. The only exception is the very top level of the window. So here's your building, and here's your windows. You have to stay 3 feet away, but if there's only 6 inches between the top of the building, otherwise, you're allowed to go up and above that one section, but that's the only instance where you're allowed to do that. All right, your raceways need to be arranged to drain. This is where that solar installer who's not an electrician won't do as good of a job as an electrician installing solar, because that electrician inherently knows that, hey, when I'm coming into a box with my conduit runs, what am I doing with my cabling and the actual location on that box of where I'm coming into it to plan for the circumstance that there's moisture inside that box that's pooling, and how does it get out? Or if it's raining, how do we make sure we're not getting water in? Exterior surfaces need to be listed or approved for wet locations. Vegetation, you are not allowed to use trees to support the solar array. That sounds kind of comical, except, hey, this is an off-grid market, and say in Mississippi, we have nothing but very tall pine trees all over the place, and so you have a clearing, but the shadows from the trees are so long, you might start scratching your head thinking, well, can I just build a structure up on those trees and get the array higher than that? And the answer is no. I think maybe with the advent of rapid shutdown that could be revisited for solar, but anyway, that's being a little silly. The raceway seal. So when entering a building from the outside, the raceway should be sealed. And it's all about, we'll see this come up later as coming in from underground to above ground, but from outside to inside as well. It governs the same thing. It's about temperature differential. So if it's colder on one side of the conduit than it is on the other, you can get condensation occurring from the humidity inside that conduit can start kind of raining inside the conduit. And so you can open up a box that's further down the conduit in terms of elevation, and all of a sudden a bunch of water comes out. In the wintertime, you might see a box that is opened up and the whole inside of the electrical box is a block of ice. And it's because they haven't done a few things. They haven't arranged their fittings to drain, and they haven't sealed, across multiple temperature differential or across a temperature differential. The number of supplies that can service a building, generally speaking, it's one. You can have one electrical service that's serving a service. So if you have your home electrical service, you have one grid connection, not two grid connections. But there are exceptions. Emergency power systems might be tapped on to their own dedicated connection ahead of everything else, so that if something goes wrong with the building and the main breaker trips, you still have the smoke detectors and the fire pumps and your emergency system still working. It might be on its own breaker or its own standalone service. And that goes true with other generators and energy generation related devices that are not loads or electrical services. They say, hey, there's these other supplies that we're going to allow you to interconnect to the building. We'll talk more about that tomorrow when we get into our interconnection discussion. The number of disconnects. So sometimes I look at service panels that look like this, and they don't have a main breaker on top. Here's a service panel that has that main breaker, and you flick that breaker and the whole panel dies. When can you use one versus the other? It costs a little bit more to buy the panel with the main breaker, and that main breaker itself costs money too. So when do you use one or not the other? Well, there's a rule called the 6-handle rule. And this rule says up to 6 disconnect switches. So this is a 2-pole, that's one switch. And here's another 2-pole, that's another. Here's another 2-pole, another 2-pole. Here's some single poles, but regardless, there's more than 6 of them. So once you have 6 disconnects in a group, any more than that, you have to group into a main. And so there's more than 6 breakers on this service panel, and so now you have to have a main disconnect. Sometimes I look at these kinds of panels and I'm like, well, wait a minute, I count more than 6 breakers on this. Generally, the top breaker is going to be the supply, and at which point you can have up to 6 breakers, whether they be double pole or single pole, all grouped and able to be disconnected at one throw switch. Or it could be that all of the circuits on this panel are solar inverters coming in from a giant utility scale ground mount array, and if there's more than 6 of them, you have to have a main breaker up top. The idea being that you can fully de-energize whatever you're around, whatever you're working on, without flicking more than 6 disconnects. However, you can have multiple groups of 6 group disconnects. And certain, if you have your load panel, if your solar power distribution panel is a separate panel, you don't count between the two. It's just at the panel itself. Anyway, 6-handle rule. You have more than 6 disconnect switches, you need to group them into a main. So we have the type of disconnect. And this is where I wish that local jurisdictions would be a little bit more lenient on the solar disconnects. Local jurisdictions will often require a knife switch disconnect for solar, being that external disconnect. And the knife switch disconnects are more expensive than, say, a breaker. But at any rate, there's multiple kinds of disconnect switches. There's disconnect switches with fuses, there's disconnect switches without fuses, there's knife switches, there's breakers. It says when you have a combination of feeders or services on site, a directory should be installed at each disconnect location, denoting all other services. So that could mean on a solar project where you have an external disconnect and an internal disconnect that you actually need to have a map showing the disconnect locations on both sides, inside and outside. The disconnect construction. So we got powered disconnects that might have a motor to open up the breaker, or a digital relay to interrupt the circuit. But the main thing is it has to have a means of manual disconnection. In the United States, we love our manual disconnect switches. And simultaneous opening of ungrounded conductors. So, let's say you have two, a leg of 120 volts, another leg of 120 volts, or let's say you have a positive and negative coming off a battery. These disconnects need to open simultaneously in many circumstances. And then plainly indicating where it's open or closed. So I came across a Marina disconnect switch that was a knob like this, and you turn the knob and it disconnects the terminals that are behind it, like a battery disconnect for a boat. Well, a knob like this does not, you can't look at it and say, well, is it in the open position or the closed position? So your disconnect switches at a minimum will have an open and a closed position to visually indicate what the knob is. But sometimes you can get into trouble if you go too cheap with your materials and start borrowing materials that are not intended to be used on a home, for your do-it-yourself project. Your disconnect switches at a minimum need to indicate whether they're on or off one way or another. Now here we get into the knife switch disconnect requirement, and this is this is in National Electric Code, and it says for circuits over 1,000 volts, a switch that has a visible break shall be installed on the supply side of the disconnecting means. Well, residential solar is not allowed to be 1,000 volts unless it's a ground mount that's detached from the building. And even then there's heightened requirements for 1,000 volt systems. But it's this visible break that says I need to be able to look at it and see how it disconnects. It doesn't mean that you can't put a dead plate on front of it and cover it up in a safe manner. It's not a code requirement to expose the users to these energized terminals at all times, but you should be, unlike a breaker where you can't see the inside of the breaker to figure out what's going on. A knife switch disconnect, you can open it up and see the gears and see the metal bars that are actually connecting or disconnecting. So that's that visible break. Up denotes on, unless it's a double throw switch where there's a middle off position and then an on position on both sides. But if it's only a kind of a two-way switch, the up denotes on. And that becomes true on disconnect switches too, where the up side inside the switch on your landing terminals, if you have a box, you're going into a terminal block on the top and a terminal block on the middle, and then coming out of the box, that top terminal side is the side that is the grid side, the side that's always on, whereas the side of the switch that is being disconnected and turning off when the connection fails, one side stays on, the other side stays off. That off side is on the bottom of the switch. And what that means is if you have the grid come in, say it's an underground service feed, and the electric grid's coming into the switch from the bottom, and then let's say you have a solar array on the roof, and you're using a Myers hub and coming down from the solar array from the top, what that means is the utility feed you have to bring around and land on the top, and the solar feed you have to bring around and land on the bottom, whether it's inside or outside the box itself. That all kind of comes from this idea that the up is grid, up is on, down is off, down is de-energized on the inside of that box. Electrical services, other conductors in the raceway. The main thing is you don't mix multiple purposes together. And so your solar array system can have all of its conductors in the same raceway, even if they're AC versus DC. They may need to be physically separated by a barrier. So in a tube, you wouldn't have that, but you can get gutters with barrier sections and keep them separated. And so you can have AC and DC in the same cable tray as long as they're in separate parts. What you can't do is combine your solar conductors with your non-solar conductors, just like they're saying your service conductors with your non-service conductors, or your devices and your loads with your power supplies. So you can't mix and match. The exception is, this is a common exception, load management. And so if I have monitoring systems and loads that have to do with the solar array operation up on the rooftop, I don't need to run those in separate cable tray. Even though they're loads and not part of the power supply, I can still share that space. Let's see, minimum sizes of services. Okay. Here we have clearances, and this is where code is starting to repeat itself, where we see, a 15-foot clearance for higher voltages and, lower clearance for lower voltages. And there's actually, in 2017, there's a discrepancy where that says if it's a non-pedestrian rooftop for the services, we can have an 8-foot clearance, whereas we just saw in the previous section for feeders, it was an 8.5-foot clearance. That's actually a discrepancy. But the reason why we're repeating is that we defined feeders, which are, how power gets from one electrical box to the next through a dedicated circuit. Now we're defining services, which is a specific type of feeder, which is power coming in from the grid, to feed that box or that electrical service at that point. Okay, so service entrance conductors, we got some conduit and protection requirements where subject to physical damage. And so it's not just about EMT tubing. There's rigid tubing. There's an intermediary tubing between the two. With your PVC piping, there's introductory PVC like Schedule 40 that is the most useful, but then there's a thicker, more industrial Schedule 80. All of this says is where you're subject to physical damage, you need to protect your electrical wiring. And so if you're planning an electrical wiring run along a driveway and you're like, well, what happens if the car hits these conductors? The answer is you have to protect it. Maybe the utility can be outside of conduit without any physical protection, in an overhead run coming into your house. But if that same power line were run along the side of a building where a car could hit it, it would not be allowed to be outside of conduit for physical protection. And that's the main thing, is conduit is there for physical protection. Sometimes there's grounding, rules about whether or not that conduit could be used as a ground path or not, but no bones about it, that conduit is there for physical protection. The service entrance conductor needs to be secured within 12 inches of its initial point into the building, and then every 30 inches afterwards. So the service entrance conductor may have some additional special support requirements that feeder conductors in general may not have. Um, individual conductors entering the buildings need to go through drip loops. And so, I might be visually offended by this, tangle of cable, but it's actually, not a tangle. It's an intentional drip loop so that if it rains, water doesn't come down this cable and go right into the building, that instead it takes a detour and drips off before it goes in. So when you're up on a rooftop, putting solar cables going from the array into the rooftop transition box, you think about the same things as well. How do I make sure that if water gets on the array components underneath the array and it's going into this rooftop transition box, where do I land on that box so that the water sheds off of it rather than goes into it? Now we're getting into breaker rules. Overcurrent protection is rounded up at 800 amps or less. So you do your circuit calculation, you have a 12 amp load, and then you apply the 25% overcurrent protection, and now you're up to 16 amps. And so you round up to the nearest breaker, which is a 20 amp breaker, and they're close enough together that you say, okay, well, we're gonna, even though the cable itself might be rated for 15 amps and it's on a 20 amp breaker, that's close enough. When you get into 800 amp services or larger, it flips around on you. They say, okay, well, now we're going to make sure, if this is like a utility scale project, an industrial facility, we're going to make sure that you're rounding down so that if the load exceeds what it's rated for, the conductors themselves are oversized as such so that they won't smolder or burn up even during a ground fault. The real reasoning behind this is that the breaker sizes are getting further and further apart, so that if you're rounding up the breaker size, there's a 200 amp difference between 800 amps and 1,000. There's only a 5 amp difference when you're rounding up to the nearest breaker size. If you kept doing that, you would be allowing way more electricity through those circuits than what the circuits would be rated for. They'd burn up. They'd get too hot. Now let's talk about taps. So taps are where, if you have a conductor that's a feeder, there's no loads coming off of it. It's from one distribution panel to the other, or it's coming from the utility and it's a service. It's a type of feeder. So on either one, coming in from the utility or actually within the building, question is, where can you just tap onto it to put your solar connection that's allowed to be tapped onto feeders? And say, well, it says you could just put it on a disconnect switch without overcurrent protection if that tap is not over 10 feet long, or what that means is within 10 feet of that point of service. So at this connection point or that connection point, you go up to 10 feet away without putting a distribution panel with fuses and breakers. You can just put a knife switch disconnect instead. It's not so hard to get a fused knife switch disconnect if you need it. All right, so the grounded conductor, the neutral wire, it says you don't put a fuse on the neutral wire. You're putting a fuse on the power supplies. You don't need one on the neutral wire. In fact, we're concerned if you do, because then the neutral wire could be opened when it's supposed to be shut and connected to ground. You open up that breaker, then there's a portion of the neutral wire that's not connected to ground. And so the only time you put the neutral wire on a breaker is if it opens all the circuits, including the neutral, at the same time. So sometimes you'll get a breaker that's like 3 poles, and the breaker bar is all ganged together so that you can only flip the breaker all at once for all 3 sections. That opens up all 3 sections of the breaker at the same time. You only put the neutral into the disconnect switch or into the fuse switch if it's simultaneously opening all the other circuits. So let's see. I keep moving along here. Grounding, service supplied alternating current systems, load side grounding connections. A grounded conductor shall not be connected to the equipment ground or reconnected to the ground on the load side of a service disconnect except in certain points. And this is where you can make a design mistake. You can be reading through one section of code and it says, hey, you have to make sure the neutral is connected to ground. And then you read another section of code and it says, hey, make sure you're not connecting the neutral to ground. And if you don't know how the role of the neutral and how it works, you can get pretty lost in that discussion. What makes things even more complicated is there are certain electric service panels where the neutral and the ground are already interconnected, where they have this bar of metal that goes between the neutral and the ground to make that neutral to ground connection. And so the problem is what if you then use that same panel again and you made another neutral to ground connection? As we can see here in this graphic, a very detailed study, we have this bar here that's connecting neutral to ground, and in this other graphic, we don't have that. Instead, the neutral is not connected to ground, and it comes all the way back to the main panel. So we need the neutral connected to ground to promote electrical flow in the system, but we need to control our electrical flow and make sure that when the system is operating normally, when we're not using our emergency effective ground path to clear out a problem, in normal operation, we don't want the electricity just to leave the system kind of willy-nilly. We want it to go all the way back to its grounded connection. And so the way that I remember this is there's one point of connection between neutral and ground on an electric service. And so if you have 2 services right next to each other, if you have the solar array doing the supply side tap on the utility side of the main breaker, and then you have the electric service panel, by itself too, that's kind of advanced jargon for if the solar array is on its own kind of supply side service and the home is then on its own service, then you might have a neutral to ground connection in the solar array and a neutral to ground connection in the home service panel. This is really a sub-panel issue. When you have one panel that's piggybacking and connected to another panel that's closer to the electric grid. When you have a sub panel off of a main panel, you don't make the neutral to ground connection in the sub panel. That neutral to ground connection should be only made once, all the way up to where that service is touching the electric grid. I think Mike Holt, he's a good I think I picked this up from him. He says, hey, if you have a bucket and there's a hole in the middle and the electricity's going out one way, then that's controlled and that's how it's supposed to happen. If you have a neutral to ground connection all over the place, then that electricity can be, it's like your bucket now has dozens of holes in it and it could just be going out anywhere. And that would mean that your ground fault current detection system, which has those computer chips inside these breakers, it can't work because now you have electricity leaving the system before it even, gets back to the panel. So your ground fault detection may or may not work if you have a neutral to ground connection being made where it shouldn't be. And then your ground fault detection indicator could be giving you a healthy thumbs up when it's really not working. And so the term for that neutral to ground connection is called the main bonding jumper. It's that main point where the neutral is connected to the system ground. Let's see. So here we're going to see this come up in our wiring discussion, but they're talking about the neutral ground conductor, and they make out this comment that says, oh, hey, if your neutral system is so large that you want to do parallel runs of cable instead of one single cable, you can, but no smaller than 1/0. And so that becomes a common just rule throughout the rest of code that says you're allowed to break up your power cables into parallel runs, but only for very large cables, 1/0 or larger. That starts to get into like welder's cable or larger. So that main bonding jumper, it might be as simple as a screw. It might be that you're taking the neutral bar and you're putting in a screw and you're screwing the neutral bar into the back of the metal box that it's inside of. And the metal box is connected to ground, and you're connecting your neutral bar to ground with that green screw. And so if you're using a screw in your service panel to connect the neutral to ground, there's a special green finish that is required to indicate that. And so now we have some questions. And these are kind of advanced electrical questions. Let's see if we can't come up with the answers to them. Does a transfer switch disconnect the neutral? So if I have a generator on site, a backup power system, if I have a switch that manually disconnects me from the grid and turns on a backup generator, am I disconnecting the neutral while I'm doing that? And the answer is, well, if you are disconnecting the neutral, so you're allowed to disconnect the neutral if you disconnect the positive and negative at the same time. So you're allowed to disconnect the neutral, but only if in that act you're also establishing a new neutral to ground connection. So if you have a generator and it has its neutral connected to ground into its own ground rod, kind of out at the generator, and you want to use that neutral to ground connection out at the generator, then you would have to disconnect the neutral to ground connection, from the main side where that switch is. Or you can keep the neutral to ground connection as is. But just the rule is only at one point on a functioning operating electric service should you have a neutral to ground connection. So you shouldn't have two neutrals to ground at different locations. You're allowed to use the same grounding electrode. Okay, so let's talk about the grounding electrode for a minute. It's that last step, that 8-foot copper rod that's hammered into the ground that your copper wiring attaches to. It says let's just we're gonna get into a little bit more detail. The grounding electrode can actually be a couple of different things. It can be a metal water pipe. If you're building a concrete foundation and you're building rebar into that foundation, it is possible to use the rebar as the ground, but it's very difficult to. What you have to do is have 20 feet of continuous rebar, not 20 feet of total rebar, but a 20-foot long stick, or otherwise not just tie wrapped, but welded together rebar for it to be considered to be good enough as a ground rod. And that's because concrete is less conductive than soil. And so, they say, well, if you're not putting a ground rod in soil, then we're going to subject you to a little bit more of a, harsh oversight. This grounding electrode is now in concrete, so you need more metal in that concrete to have equivalent conductivity. Similarly, it's common in grounding to use a number 6 bare copper wire. Sometimes it can be even smaller than that, but number 6 is very common for 200 amp electrical service. They say if you're going to use, if you don't have 20 feet of rebar, there are certain circumstances where you can use bare number 6 as your grounding electrode instead of a ground rod. But if you're in concrete, they're saying you got to use number 4 as the minimum size if you're using copper wiring. So when can you use bare, copper wire as the ground? Well, you could circle the whole building with number 2 wiring. Usually that results in a higher cost, but not all soil is good for ground rods. Some soil is not very conductive. Dry soil is not very conductive. Rocky soil is not very conductive, and nor can you dig down very deep. And so it might be that to actually get good grounding, that you have to implement a much larger ground ring in very extreme soil types. If you're building your on top of a rock shelf, you might not be able to chip much rock out of there. But for most soils, we're using a ground rod. That ground rod should not be less than 8 feet in length. It can be, you're running the copper wire up to the ground rod. I get really concerned about this connection over the long run. On a recent project, we were using CAD welding, which is a little old school, but we were actually welding this connection rather than relying on the bolt. And I thought that was, once we got the hang of doing CAD welding, I thought that was a better way of doing it. Although finding the actual CAD weld is the difficult part. Okay, so there are ground rod resistance tests. And if you aren't testing 25 ohms or less, then you put in a supplemental ground rod. I think putting a supplemental ground rod in anyway is not a terrible idea. It's good to have some redundancy. You can't have a redundant neutral to ground connection, but you can have a redundant ground rod. The thing is, if you're putting in 2 ground rods to improve resistivity, you should note that electricity to ground is being dissipated over a surface area, and the ground rods, if they're right next to each other, won't increase your resistivity unless they're spaced apart. So, required additional grounding electrodes need to be spaced apart. But you're also allowed to put in auxiliary grounding electrodes that are just purely redundant, so that if one connection to one ground rod fails, you're still connected, and those aren't subject to the same rules. You'll have one ground rod per building. So it says, when not exposed to physical damage, number 6 or larger is permitted to be run along the surface without building protection as a grounding electrode. So where this comes into play is up on a rooftop. You got your solar array, and you have your solar rails kind of running across the rooftop. The question is, how do you ground the metal solar rails and the metal module frames? And the answer is, well, you run a ground up there. And so here's our grounding electrode, on the side of the building. There's different ways you can run your DC ground through the home. What I commonly do is I combine the DC ground with the AC equipment ground conductor and run the DC ground through the equipment ground conductor down to the ground rod itself. So I'm running my ground back to the inverter, and then I'm taking the inverter ground and the AC out, running it with my AC output circuits, and getting back to the house that way. The main thing when you're piggybacking off the AC equipment ground is that there's sizing requirements for the DC side ground, and there's size requirements for the AC size ground, and you just need to check to make sure you're using the larger of the two. And so if the smallest DC grounding electrode size is number 8, then you need to make sure, if you're using the AC equipment ground conductor as your DC pathway to ground as well, then it needs to be sized to accommodate that number 8. Sometimes these AC equipment grounds can be a little bit smaller than that. An alternate common solution, and so I'll usually run my ground as number 8 up to the rooftop internally. Another common solution, though, is just to go one size up into number 6 and just run your number 6 cable from the ground rod, straight up the building and onto the roof directly. And you can just run it in bare number 6 by itself without protection, without conduit. You can run bare number 6 alongside the building, provided that it's not exposed to physical protection, such as running along the side of a driveway. There's a difference between the side of the building or a place where there's higher likelihood for physical damage. And this DC electrode should be continuous. So, what that means is that run from the array rack on the DC side to where it might land onto the AC equipment ground conductor needs to be a single piece. Or the run from the ground rod up to the rooftop needs to be a single piece. If you do cut it, then there's certain rules about crimping it back together to essentially ensure that you don't ever disconnect the ground of the system. Now, what would happen if you disconnected the effective ground path of a system? Well, if your solar panels started faulting into the metal module frames, and those metal module frames were not grounded to anything, they would just have high voltage, and it's likely that nothing would happen. Well, that sounds pretty good, right? Nothing happens, so no fires are breaking out, no electrons are flowing. Well, yeah, but it's a death trap. I mean, if someone is walking along the roof and they have enough resistance to ground and they touch that high voltage module frame, they could electrocute themselves. So, we want faulting electricity to be able to have a path to ground, even if that might mean, bad things are happening. They shouldn't be happening to begin with, and we're trying to manage, that failure point. Okay, so if you're running to a ground rod or a ground pipe or a ground plate, your ground does not need to be any larger than number 6. So another reason why number 6 bare is commonly used as a ground is it is like a one size fits all solution. If you're using, it's common to use a ground rod or ground plate, and so you do your calculations, and it says your ground needs to be so large. If you have a ground rod or ground plate, code says it doesn't need to be larger than number 6. This can commonly get overruled by local jurisdictions to say under no, under that's fine, but in our grid, it's a 200 amp service, and we're going to require you to have a number 4 ground. They might not allow you. A local jurisdiction rule would say you're not allowed to use that exception. And I've come up across it, and I've asked the inspector about it, and his response was, well, in this region, our soil doesn't get very good resistivity, and so we want to make sure that it's everything is sized to the max. Okay, that ground rod doesn't, that the grounding electrode conductor, the thing that connects the service panel to the actual ground rod itself, that doesn't go down in the soil. But anyway. So there are rules that govern the minimum size of your grounding electrode conductor, they're basically based off the size of the feeders going into the home. That says, hey, this 2-aught to 3-aught cable, that's capable of holding this much amperage. And so, we're not requiring the ground path to be of equivalently sized amperage, but there is a minimum that we do require. And so solar, we're normally dealing in like number 10 cable or number 8 cable. And this is saying if your service entrance conductors are number 2 or smaller, you can use a number 8 ground. And this is, commonly for residential size solar projects, the smallest ground that you need is number 8. Not too hard to upsize it to number 6 and avoid the need for running it through bare copper, or through conduit. You can use bare copper instead. And then, but just keep in mind, when you start getting into 200 amp services or larger, the size of that grounding electrode conductor does in fact increase. Unless you're using one of the exceptions, and of course that would require the local jurisdiction not to have any special rules. Okay, this is a good one. What we're seeing is conduit coming into a box. And so when I got started learning about electrical, I was like, okay, well, we got metal conduit, and the metal conduit goes into a metal box, and that means the metal conduit can be used as a ground path. And I'm looking at the metal water pipe being used as the grounding electrode, and I'm thinking, man, we're using the metal conduit as a ground path all the time. That's not really true. Often you'll run a equipment ground conductor inside that metal conduit so that you don't have to worry about it being the ground path. And the reason is there's certain conduits, there's certain metal conduits that are not registered to be an effective ground path. Like if it's not a clear continuous stick of tube, but is instead kind of a spirally flexible coily cable, it might not be rated for a ground path. The box itself matters as to whether or not this is grounded or not. So you got your metal conduit and it's coming into this box, and we got these holes in these boxes. But see in the background here, we have a hole that has different sizes. There's an inner hole and then another hole and then another hole. And that's so that it's easy to have a hole of different sizes in the box. Go figure. Well, this is also an impaired connection in the box. That little dimpling of the metal reduces its resistivity. And what that means is if I want to have metal going into a metal box with a regular lock nut and nothing special going on, that only constitutes a grounded path if I'm using the outer ring of that box. If I'm using the inner ring, then I still have that dimple. It's still an impaired connection. If I'm using the outer ring, it's continuous and smooth. And what happens is if you're going into, say, a plastic box, or if you're going into an impaired connection, you can buy these little lock nut attachment points that come with a little terminal to run some copper wire to, so that you ground the conduit. That metal conduit needs to be grounded one way or another. So you're either grounding it to the box or you're grounding it to a piece of copper that comes and then lands on a ground bar inside the box, and other grounds can be coming off of that as well. So impaired connections cannot be ground paths. You have to make sure that these couplings and fittings are made up tight. If they're loose, if they're not tight, they're not going to be an effective ground path. And says MC cable is acceptable. We're looking at some grounded conductors. We got there's various different kinds. Well, we're going to save that for a wiring and conductor discussion. One important thing to know is you'll be on site and seeing equipment grounds that are in a green jacket. And again, it's number 4 or larger can be taped green. Anything smaller than that, other than bare copper, has to be in a green jacket if it's the equipment ground conductor or the ground wires. So a lot of these projects, the difference between a do-it-yourselfer and a professional contractor is going to be, for cables that are number 6 and smaller, are they using colored cables or not? Are they organized enough to not just buy one big spool of black cable and that's it, or are they buying the actual spools needed for the job as they go? That can also be an indicator of how much business they do, for that matter. If you are increasing your cabling sizing, then you'll need to increase the size of your equipment ground conductor, unless you're using a ground rod with bare number 6. It's sized for the highest amperage device along the raceway. So now we're looking at not the grounding electrode conductor, but the equipment ground conductor. So remember, the grounding electrode is the final stop on the station. Then you get to your service panel, and all the other grounds that come off the service panel, usually there's a little bar that they're all wired into. Those circuit level grounds are the equipment ground conductors, grounding all the equipment back to the service panel. And so these are based off the breaker size rating. It'll size the equipment ground conductor and so I guess what I'd say is a lot of solar is on 40 or 50 or 60 amp circuits, and its minimum equipment ground conductor size is number 10. Um, you might get an inspector that says, I also want to see a DC side grounding electrode run up to that rooftop. And then the minimum size when using a ground rod is number 8. So often this leads to a material discussion we have in other classes over good material selection. I'll do an MC metal clad cable, and I'll upsize that to number 6 because it comes with a number 8 ground. And then I have all of my grounding requirements as well as solar cable all bundled in one flexible cable that I can easily run through an attic space. So we're going to talk about that. Might be first thing tomorrow. So we have direct current systems that are less than 300 volts should be grounded. But greater than 6, we're going to talk about that when we get to the solar and battery sections tomorrow. The size of the DC grounding electrode, it's kind of the same rules as the AC electrode. Not smaller than number 8. Ungrounded DC separately derived systems shall have a grounding electrode conductor connected to the electrode. Not all solar systems are separately derived, but all this is really saying is that if you have standalone systems, they all still need to be connected to the building ground one way or another. And it's all metal parts, all enclosures, all boxes, all raceways. All exposed non-current carrying metal parts need to be connected up to the grounding system. Okay, so we made it through the first half of electric code, which is section 200. We're getting into wiring methodology. Let's spend a few minutes on this, make some headway, make sure we have enough time for solar and batteries tomorrow. We have so these are wiring methods, and here's one for going through wood members. So contractors will run power through the studs and through the beams, and it says, okay, you have to be 1.25 inches away from the nearest edge of the wood member. Otherwise, you need to put a steel plate on that wood member, basically to prevent people from drilling into the wiring. If you're drilling in, mounting something on the wall, you could be drilling it into a stud, and you have to be stepped back from that by 1.25 inches. Similarly, when you're running underneath the roof, you need to be over 1 inch from the underside of that roof surface. And so if you're in the attic and you're running your conduit along the rooftop, you can't just put it right up next to that roof deck. You need to give yourself a little bit of room, to imagine that someone down the line is hammering a nail through, giving yourself some damage, some room. Here's another one, warning ribbons, so that when you're doing underground work, putting cables and conduits and anything underground, when you're filling in that trench, you need to put a warning ribbon so that people, if they're digging in that area, the first thing they encounter is the ribbon and not the electrical devices. It's kind of interesting. You can splice and tap a cable without going into a box for underground. Backfill, you don't want any rocks or sharp objects. This is the kind of a debate in the electrical industry. Do you do conduit or direct burial cabling? Direct burial cabling is so much easier than going into conduit that power companies do direct burial all the time. But it really depends on what your backfill is going to be and then what's on top of it pressing it down. So when you're going over roadways or motorized areas where you have heavy machines on top of the surface, then you might have a need for more physical protection. And then you have to account for earth movement in areas where you have freeze thaw conditions and you're going from frozen ground up to non-frozen ground, having expansion fittings and S-loops, expansion fittings for thermal expansion on the rooftop for that matter. All right, so now we have raceways exposed to different temperature differentials need to be sealed. We have a requirement for electrical continuity of raceways. So we already saw, entrances needing to be sealed in section 200. It's repeating it again in section 300. This is a useful one. Short sections of raceways used to provide structural support or protection do not need to be part of the electrical continuity section. So if I have a footing, if I have a pipe boot and it has a piece of unistrut on it and it's supporting some conduit that's running across the top of the rooftop, how far does this grounding stuff go? Do I need to ground the all thread and the unistrut and the pipe boot? It says support sections. And even you could argue that if you have a box here and a box here, a little 6-inch tube that connects the two together would similarly be a short section for physical protection. Are generally not subject to the same temperature derating and conduit sizing considerations that larger, anything more than a foot, I'd say. Here it's kind of saying, so that's kind of interesting. You don't have to overkill your concern about electrical metal continuity. With AC side stuff, you have to be a little bit concerned about the space between individual conductors going into metal because of induction. DC is not, that's not a concern. There's also requirements in this section for conductor bend radiuses, and I think that can kind of mess up a designer where you have to account for the actual size that it takes to bend the wire around a turn. And that might mean, if you have a large box with a sharp 90-degree turn, you have to use the large box and not the small box. It can also mean when planning your space requirements where your conductors and stuff come down, you have to start planning, your space for the bends. This is just common workmanship that electricians do, standard practice. Again, we see the parallel requirement for 1/0 cable for the conductors in parallel. And the main thing when you are dividing into parallel runs is that the raceways, the individual divided out sections, have the same characteristics. You don't put all of your leg ones in one conduit and all of your leg twos and grounds and neutrals in another. You divide up the amperage evenly, you divide up your neutral evenly, you divide up your ground evenly. Well, look, we've made it 3 hours into this program, and we have another part 2 tomorrow. So what we're going to do tomorrow is talk about temperature derating considerations for circuitry, and then transition into a battery and solar discussion. So we're halfway through class. There is a quiz afterwards. I'll let Lane explain that a little bit. Lane, I might need to say a few comments when you're done with your section. So I'm going to pass it back to you. And I'm going to, while Lane's talking, I'm going to briefly look at the quiz to make sure we covered everything.
Okay, yes, there will be a follow-up quiz actually after tomorrow's presentation. There won't be any quiz to complete for today.
Okay, then never mind.
So yeah,
take it away, Lane.
Okay. Well, actually, so with the break, I'm seeing that the agenda for both days actually goes till 2:15.
Oh yeah, no, I'm sorry. Let me use that time then. Because
okay. Otherwise, if it works better to like as far as addressing certain topics, we could always add that onto tomorrow's.
I think if we do, I mean, I know people. I already rung the bell on class, so I'm sure people are wanting to get out of here. But if we spend, my classes are pretty compact, so if we do spend another 10 minutes talking on this, that'll mean we'll have that much more time tomorrow to spend on the solar and battery components. So I'm just going to keep going, and I'll kind of start wrapping up around 10 after.
Okay, great.
Okay, so we were talking about similar characteristics within raceways if the conductors are wired in parallel. Then we start getting into temperature degradation. So it says ampacities for conductors that are under 2,000 volts. And it says, look, we have to consider a few things. What's the temperature outside? What's the temperature because of the circuitry? The same temperature that opens up the breakers is inside those conductors. And those conductors will, they're wrapped in some plastic, but they will radiate heat. And then what's the heat dissipation rate? If I put all these conductors inside a conduit that's enclosed for physical protection, now I've eliminated the airflow around the conductor and put a whole bunch of conductors in there. So, if there's a conduit that is full versus a conduit that has more empty space, and then just the nature that it's in conduit, all those things are going to increase the temperature on that conductor. And so all of these things will impact the ampacity of the conductor. And then after you get that, you might apply, an additional 25% protection to whatever this spits out. Or you could, as an electrical engineer, you may be allowed to perform the actual calculation and stamp it to say, actually the temperature derating is not going to be that bad. I know precisely what it's going to be. The temperature correction factors in code are to get around doing engineering calculations, so that electricians don't need to know the math, but can still install electrical devices in a safe manner. Okay, so we have some adjustment factors. The first is if there's more than 3 current carrying conductors in a conduit. And then I say, look, short sections, this does not apply to. We're not concerned if there's a box and another box, you're just doing a short run and running all your cables from one box to the next. We're not concerned about the temperature adjustment in that situation. We're concerned about the conduit, that's going, 100 feet, 200 feet in the other direction, on what the temperature differential is going to do to this center cut, the least amount of airflow. So this ampacity derate does not apply to those short sections, near the inverter wall, but rather the long sections between the inverter and the array, or between the inverter and the point of interconnection. This is kind of interesting. It can apply to underground cabling if they're not spaced appropriately apart. And so in commercial design work, you're going to get spacers for your conduit conductors that go down into a trench to space them out enough for better heat dissipation. One of the other items that's been bouncing around in code a whole bunch, and it continues to be changed, is the temperature for thinking about ambient temperature. A rooftop is the hottest part of the building. It's hotter on the roof than it is in the attic as far as maximum temperatures go. And so we have outside of conduit cable in solar on the rooftop, and it can be exposed to direct sunlight. But on top of that, you would also have conduit on the roof being exposed to direct sunlight. And it says, so if we have raceways or cables exposed to sunlight, direct sunlight on the rooftop, you need to have a 1 inch, or technically greater than 7/8 inch. You need to have a 1 inch clearance up off of that rooftop. If not, in most circumstances, you can maintain that 1 inch, but there are certain, special circumstances where you may not. Let's say that your cable is already oversized to accommodate the ampacity after the temperature derating. So you're already oversizing your cable, maybe not for amperage, but for voltage. And so if you're already oversizing your cable because of voltage, you might have the amperage that you need to adjust for the temperature differential. And then you'll say, okay, well, I'm just going to stick to the rooftop. But there's devices you can get now in the solar industry to support cable and conduit up off of the rooftop, even while you're making those runs. If you don't maintain that 1 inch clearance for whatever reason, you have to add 60 degrees to the temperature differential. And so we're going to take a closer look at that, but that is quite a steep temperature adder. This section of code used to be 0 to 1 inches, and then 1 to 3 inches, or 1 to 4 inches, and then above 4 inches. And they had different derate factors for the like. Since then, they've gathered more data and said, you know what? There's really not much difference between 4 inches above the roof and 1 inch above the roof. And so we're going to simplify things. And now, instead of being a table, it's just 1 inch above the roof. You're good for not adding temperature, as long as you just designed it ambient, and that's fine. But if you're right on top of the roof, you're collecting more heat from that rooftop, and we need to increase the temperatures accordingly. The neutral wire in this case does not count as the current carrying conductor, because that neutral is only going to be carrying the imbalanced load between the two loads, and your load A and load B. That neutral, when it has current in it, is going to have less current than if the two power cable conductors were at full blast, evenly balanced. So it doesn't count as a current carrying conductor. Neither is the system ground, for that matter. And so you count up your current carrying conductors, and it can result in a discount. If you have 20 or more conductors crammed into a single conduit, you could be discounting your ampacity by over 50%. So where we will kind of end with is that there are tables in National Electric Code that can be a little intimidating at first glance to read, that say, okay, well, we have our conductor temperature rating, And different cables have different temperature ratings. Solar cable tends to be on the high end of the temperature rating. Sometimes indoor AC Romex, might have a bare minimum temperature rating because it's not designed to be used in high temperature environments. Underground cables that are just standard may have a higher temperature than an indoor cable. So that comes into cable jackets, and that's included in the code. We're just not there quite yet. So we have the temperature condition of the jacket, and then we have the actual temperature that it is outside. Our operating environment. Are we in a freezer or are we on a rooftop? And you say, okay, well, the conductor is sized for, let's just go down. This is 90 C temperatures. And the last thing is this final key here that says it's based on a 30 C or 86 degree Fahrenheit design condition. And this is really confusing, but the ampacity tables from code, when they give you the ampacity capability of the conductor, they're giving it to you at a particular temperature. So you'll have a table of all the conductor ampacities, and it'll be like, this is all the ampacities at 86 degrees Fahrenheit. Well, I'm not at 86 degrees Fahrenheit. I'm up at the rooftop at 160 degrees Fahrenheit. And so this temperature correction factor table says this is where you adjust the ampacity based off ambient temperature. It says if your normal ampacity is X at 86 degrees Fahrenheit, then if you're installing at 160 degrees Fahrenheit, then you need to discount that ampacity by almost 70% because you're at such a higher temperature. Or you could use higher temperature rated cable, and then you'll only need to discount it by not so much, by 40% instead of by 70%. And they're saying, okay, when with the 60C conductor, we're not even going to allow you to consider using it in this high temperature environment. And so these temperature, to kind of conclude our program today, these temperature correction factor tables are first step. You get the ampacity from a different table, and you look up at the table title and you say, okay, well, this is the ampacity at 86 degrees Fahrenheit. And then you go plug it into the 86 degree Fahrenheit temperature correction factor table to get your temperature correction factor based on the temperature rating of the cable that you're using. So, it's a connecting point A to point B to point C to get your temperature correction factor, but it's really not any more complicated than that. So lastly, in context of the cables being within 1 inch of the rooftop, where does that 60 degree Fahrenheit temperature addition get you? And it's saying, okay, well, if I'm at a maximum rooftop temperature of 130 degrees, and then I add 60 degrees to that, that would be, normally I'd be discounting the ampacity of those conductors by 25%. Because of the added temperature, but now I'm discounting them by a whopping 70% because of temperature. And it might also be the difference between being able to use 75C cable on the rooftop and, if we add 60 degrees, we're off the chart. We don't have an option down here, that could be indicating that 75C rated cable 1 inch from a roof surface would be beyond its spec, and that could cause a fire. So it's that having your cables be 1 inch to the roof adds a tremendous temperature adder to that should be avoided if possible, and only utilized if you are very well familiar with your design and you know that your cables are so large that even if you're discounting them by 70%, you still have the ampacity clearance that you need.